Hello everyone, I welcome you all to the 10th lecture of Structure of Atom. I am Varad Daoo, a doctoral student and also a Prime Minister Research Fellow at the Department of Chemical Engineering at IIT Kanpur. So in the last class, we have studied about the advantages of Bohr's model, right? And certain explanations which could only be explained by Bohr's models and could not have been explained by other previous models, like for example Rutherford's or some Thomson's model. So we were using these concepts of Bohr's model. We established that we were able to successfully explain why multiple lines are present in the emission spectra of hydrogen atom, right? Further, we also found out what is the Bohr's radius for the nth orbit and the velocity expression for electron in the nth orbit. Further, we also solved some 4 to 5 examples which could explain the how to apply these expressions which we derived in here, right? In today's class, what we are going to study is we are going to study the concept of quantization of energy given by Bohr, right? And then further, we are also going to study the limitations of Bohr's model and how these limitations arise. Like for example, we are going to study about the uh, uncertainty principle given by Heisenberg and dual particle nature, dual wave and particle nature of matter, right? So that is what we are going to study. So let us begin. Structure of atom. First topic is Bohr's theory and concept of quantization. So noticeable achievement of Bohr's theory of structure of atom was that it could predict the values of energies which an electron can have while revolving around the nucleus of hydrogen atom, right? So just say A. Bohr's theory could predict the energy of electron in the nth orbit, right? According to Bohr, the electron in the hydrogen atom can have energy values given by the relationship, right? So energy of an electron in the nth orbit, this has to be in subscript, is equal to minus 13118 divided by n square kilojoule per mole, where n is equal to 1234, right? It should be a whole number. So in other words, n cannot have a fractional value, so that the electrons cannot have all possible values of energy, but only those values for which n is a whole number, right? So we also concluded this, right? That energy is discretized, energy is discretized and not continuous, right? For electron, right? Thus, electron can only take certain fixed values of energy. It means that when an electron gains or loses energy, it does so in such a way that n has a value which is a whole number, right? So in other words, electron does not gain or lose energy in a continuous manner, but in jumps, right? So this led to the concept of quantization of energy, which means that the radiant energy is emitted or absorbed in burst rather than continuously, right? From above facts, we can conclude that the energy of an electron is quantized. In other words, electron does not gain or lose energy in a continuous manner in jumps, right? What does this mean? This means this led to the concept of quantization of energy, right? So let me write this. Quantization of energy, right? This means that radiant energy is emitted or absorbed in bursts or jumps rather than as continuous process. This is very important. From above, it can be concluded the energy of electron is quantized. Right? The quantization concept may seem to be mysterious, right? But it is very easy to understand, right? So if you take this as a grid, the discrete energy levels in Bohr's model may be compared with the steps of a ladder, right? Right. So let us consider this is the first step of ladder, second, third, fourth, or you could also say that these are the energy levels. Uh, Actually, as we go up the energy level, the gaps in the energy decreases. However, which is not shown in here. However, you can consider it, right? So imagine a ladder having the steps labeled as this 1, 2, 3, 4, and 5. So your position on the ladder can only be a step and never in between, right? So these steps in the ladder are similar to the energy levels or orbits in atom, right? The we can do like this. The discrete energy levels, the discrete energy levels, right, in Bohr's model may be compared with steps of ladder. And imagine a ladder having steps labeled as 1, 2, 3, so on and so forth, right? So your position on the ladder can only be a step and never in between, right? That means you can be in a ladder 1 or ladder 2 or step 1, step 2, step 3, but you cannot be at a step 1.5 or 2.5 or 3.6, right? That is what we mean by this, right? So these steps in the ladder can only be step sorry so these steps in the ladder are similar to energy levels or orbits in an atom, right? So let us move on to the next topic, that is the limitations of Bohr's atomic theory. So even though Bohr's atomic theory was able to predict and explain many behaviors, it still failed to explain some experimental observations, right? The limitations of Bohr's atomic theory. Right? So Bohr's theory of atomic structure was quite successful in explaining the stability of atom and the line spectra of hydrogen atom. However, several discrepancies were observed in this model. Some of the limitations of Bohr's model, right? So the first limitation of Bohr's model was Bohr's model of an atom could not account for the finer details, right? For example, duplet, that is the two closely spaced lines of the hydrogen spectrum observed using sophisticated spectroscopic techniques, right? So it could not explain the very close two lines which are very close in atomic spectra of hydrogen, which were which experimentally were obtained using the complicated or sophisticated experimental measures, right, or spectrometers, right? So Bohr's model of an atom, Bohr's model of an atom could not account for the finer details. Like for example, duplet. Let me use a different color for this. Duplet, which are two closely stretched lines of hydrogen spectrum observed during the observed using the sophisticated or very accurate spectroscopic method techniques, right? So Bohr's model of an atom could not explain the, so the second point is the Bohr's model of atom could not explain the line spectra of atoms containing more than one electron, right? According to Bohr's theory, on one and only one spectral line can originate from an electron between two energy levels. But if a powerful spectroscope is used, certain single lines are found to split into a number of very closely related lines, right? The existence of such line could not be explained on the basis of Bohr's theory. It is the second drawback of Bohr's theory was that Bohr's model of an atom could not explain the line spectra of line spectra of atom, line spectra of atoms containing more than one electron, right? According to Bohr's theory, one and only one spectral line, one and only one spectral line can originate from an electron, right? Can originate from electron, right? So originate from an electron, right? Between any two energy levels, between any two given energy levels, right? But if a powerful spectroscope is used, certain single lines are found to split into are found to split into a number of very closely related lines, right? And the existence of such lines could not be explained based on Bohr's theory, right? The existence of such lines could not be explained on the basis of Bohr's theory. The third drawback of this Bohr's model was that the Bohr's theory failed to account for the effect of magnetic field on the spectra of atoms or ions. It was observed that when an atom emitting radiation is placed in a strong magnetic field, each spectral line is further split into a number of lines, and this phenomenon is known as Zeeman effect, right? So it could not explain this Zeeman effect. So Bohr's theory failed to account for the effect of magnetic field on the spectra of atoms or ions, right? It was observed that when the atom emitting radiation is placed in a strong magnetic field, each spectral line is further split into a number of lines, right? And this phenomenon is known as Zeeman effect. So it could not explain the Zeeman effect. The fourth drawback was Bohr's theory also could not explain the effect of electric field. Right, similar to magnetic field, it could not also explain the effect of magnetic field on the spectra of hydrogen atom. Right, and this effect is called as Stark effect. Right, Bohr's theory also could not explain the effect of electric field known as Stark effect on the spectra of atoms. Right. The fifth one is that Bohr's theory does not provide any clue to explain the shapes of molecules arising out of directional bonding between the atoms. Right. So Bohr's theory does not provide any clue to explain the shapes of molecules arising out of the directional bonding between the atoms. Right. This was also one of the major drawback. Bohr's theory does not provide any clue to explain the shapes of molecules arising out of the directional bonding between atoms. Right? The sixth and the major drawback of this model was the main objection to Bohr's theory came from the new principle, namely the dual nature of matter and uncertainty principle. Right? So they introduced the idea that a wave character of electron, in addition to its particle character, and pointed out that the path of the motion of electron cannot be well defined. Thus, this overruled the Bohr's idea of well-defined circular orbits. Right? So this dual nature of matter said or predicted that we cannot define the path of electron precisely. However, Bohr's atom precisely told that the path of electron will be a circular orbitals, right? So this was the major blow to Bohr's model. Thus, we find that Bohr's model was only partially successful. It explained some experimental results, but was unable to account for many other features of the atom. Therefore, it was abandoned in the light of modern ideas regarding the wave characteristics of matter. Right? The main objection to Bohr's model. Bohr's model or Bohr's theory came from the new principles, namely the dual nature, which we are going to study, right? And uncertainty principle. Right? They introduced the idea, they introduced the idea of wave character of electron, right? In addition to its particle nature. In addition to its particle character. And pointed out that the path of electron, uh, path of motion of electron cannot be well defined. Right? Thus, this overrule the Bohr's idea of well-defined circular paths. Right? And hence the Bohr's, because of these many limitations of Bohr's model or disadvantages of Bohr's model, this Bohr's model was abandoned and a new model was proposed. Right? So now what we are going to study is we are going to study the dual nature of matter, right? And the experiments which proved it, right? So, model what we are going to study is modern concept of structure of atom, which is quantum mechanical model. To overcome the shortcomings of Bohr's model, attempts were made to develop a new, suitable, and general model of an atom. So, two important developments which contributed significantly in the formulation of new models were: number one, the dual nature of matter, and the Heisenberg's uncertainty principle. Right. So, let us first study the dual nature of matter. Dual nature of matter. So Einstein had suggested that light can behave as a wave, as not only as a wave but also like a particle, right? In his dual character. In 1924, de Broglie suggested that just as light exhibits wave and particle properties, all microscopic materials, all microscopic material particles such as electron, protons, atoms, and molecules, they also have dual character, right? So they behave as a particle as well as a wave. This means that an electron, which has been regarded as a particle, also behaves like a wave. Thus, according to de Broglie, all material particles in motion possess wave-like characteristics. Right? So let me write this down. Right. So what de Broglie suggested in 1924, in 1924, de Broglie suggested that just like light exhibits wave and particle properties, right? Wave and particle properties. So does all other microscopic material, right? Microscopic material particles, right? Or microscopic material particles such as electron, protons, atoms, etc. have also dual character, right? They behave as a particle as well as a wave, right? They behave as a particle and as a wave, right? This means that an electron which was which has been suggested regarded as a particle also behaves like a wave, right? Then according to de Broglie, all material particles in motion, right? This motion word is very important. All material particles in motion possesses wave characteristic, right? So according to de Broglie, the wavelength associated with the particle of mass m moving with velocity v is given by, right? So I will write. So according to de Broglie, the wavelength associated with a particle of mass m moving with velocity v, right, is given by the relation, right? Lambda is nothing but h by mv, which is lambda by p, right? H by p, sorry, because mv is nothing but momentum, right? So p here stands for momentum, right? Where let us write h equal to Planck's constant, p is equals to velocity, e is nothing but mass into velocity, which is momentum, right? And these waves are called as de Broglie waves, right? So now you see that from this expression that the wavelength is also is inversely proportional to the mass, right? That means more the mass, lesser the wavelength, and lesser the mass, more is the wavelength. Hence, for a macroscopic objects like uh, anything beyond electron or proton, the mass is so high that the wavelength becomes less, and hence the particle nature of matter becomes dominant over the wave-like nature. Whereas for mass of subatomic particle level, that is proton and electron, the mass is sufficiently low that the particle nature is not dominant. However, wave nature becomes dominant over particle nature of time, right? So now let us derive the de Broglie's wavelength formula, right? So this expression, let us derive derivation of de Broglie relationship. Okay. The relationship may be derived by combining the mass energy relationship proposed by Max Planck and Einstein, right? So the relationship may be derived by combining the mass energy relationship proposed by Max Planck and Einstein, right? So according to Planck, photon of light having an energy, right? Photon of light having energy E is associated with a wave of frequency mu, right? And this energy would be going to E is equals to h nu. Whereas according to Einstein, the energy would be E is equals to m into c square. But the energies are same, right? That means equation 1 and 2 equating equations 1 and 2 we get h nu h into nu is equals to mc square, right? But we know v into lambda is nothing but c, right? This is frequency, right? That means frequency is nothing but c by lambda. Hence we put this hc by lambda is nothing but mc square, right? That means h by lambda is m into c, right? Which implies lambda is nothing but h by mc, right? This expression is valid for photon, right? Moving with velocity c. This expression is valid for a photon moving with velocity, which is nothing but speed of light, right? But if we exchange this with a particle of mass m and its velocity v in place of velocity of light, then the equation would become this one. So, de Broglie suggested that on substituting the mass of the particle m and its velocity as v in place of velocity of light, the equation can also be applied to material particles, right? And the expression then will become lambda is equals to h by m into v, right? This expression is known as de Broglie's equation, right? Now, let us move on to the next topic, which is justification for dual nature of electron. So this was given by the Davis and German's experiment of interference and diffraction, right? So let me grab an image, right? So before that, the particle and wave nature of electron can be justified on the basis of following observation, right? A particle nature, right? So dual nature means we should have a particle nature, an experiment which correctly justifies that the electron is nothing but a particle, and then at the same time another experiment which justifies that it's a wave nature, right? So that is what we are going to study, right? So particle nature electrons. So let me first drag a figure. So in this figure depicts the electron diffraction experiment performed by Davis and Germer, right? So electrons exhibit the characteristics of particle. They have a definite mass, right? When the electron strikes a zinc, so this is for the wave nature of light, right? So wave nature. So the wave nature of electrons was experimentally verified by Davis and Germer in 1927 and George Thomson, right? So this is called as Davis and German experiment. Let me write it down. Davison and Germer's experiment showing interference and diffraction. So Davis and Germer subjected the streams of, right. So this is a monochromatic, the subjected streams of electrons, right, from a tungsten filament. So this is a tungsten filament and beam of electron was ejected from here, right. The influence of electric field so as to accelerate the speed of electron. When these electrons were made to strike against the nickel catalyst, the concentric dark and bright fringes were observed, right. So these are the dark and bright fringes which were observed, right. So these rings were called as diffraction ring, and the phenomena was called as diffraction, right. Diffraction. This diffraction pattern of electrons by crystals was similar to that observed for the X-rays, right. So what was observed for the X-rays? So the pattern which was observed for X-rays was this, right. So this was the pattern which was observed for the X-rays, and similar pattern was observed for the electrons, right. The diffraction pattern of X-rays and that of electrons are this. So this is the diffraction pattern of X-rays, and this is the diffraction pattern of electrons. The similarity of these two patterns indicate that the electrons behave like X-rays, right. This indicates that electrons behaves like a wave, right. Since X-rays have wave characters, therefore the electrons must also have a wave character, right. Moreover, the wavelengths of electrons are determined by the diffraction experiments which were found to be in agreement with the values obtained from the de Broglie's experiment, right. Right. The particle nature of matter, that is electron, had been established from a number of experiments, and its wave character was confirmed by diffraction and interference experiments. Right. The wave-like character of electron help in making electron microscope, which is very powerful tool in modern scientific research area, because it achieves a magnification of around 15 million times. Right. So let us do the next page. Right. From this, we conclude that the electrons or subatomic particles not only have a wave-like behavior, not only have a particle-like behavior, but they also have a wave-like behavior, right? So now let us understand the significance of. Although the dual nature of matter is applicable to all material objects, but it is significant for the microscopic bodies only, right? Because we know lambda is nothing but h by mp, and it is inversely proportional to the mass, right. So for large bodies, the wavelength of the associated waves are very small and cannot be measured by any of the available methods, right. So let us write this down. For microscopic or large bodies, the wavelengths of the associated waves cannot be measured by any of the available methods. Now why is that? Because they are very small. Therefore, practically these bodies are said to have no wavelengths. Thus, any material body in motion can have wavelength, but it is measurable or significant only for microscopic bodies such as electron, proton, atom, or molecule. Right. So this may be. So we are going to show you that the wavelength of electron. Right. Let us calculate the wavelength of an electron with mass of 9.11 into 10 raised to power 6 meter per second, right. So for that, the wavelength would be h by mv, which is 6.626 10 raised to power minus 34 divided by 9.11 into 10 raised to power minus 31 multiplied by 10 raised to power 6, which comes out to be approximately 7.28 10 raised to power minus 10 meter, right. And that for on the other hand, for let us write this for microscopic, right. For microscopic particle. This is the de Broglie wavelength, and for macroscopic particle, the de Broglie wavelength is going to be, we are going to calculate, right, the wavelength associated with a ball, for example, right, with a mass of 10 gram and same velocity. Let's say the velocity is 10 raised to power 6 meter per second, right? So for that, lambda is going to h by mv, which is 6.626 10 raised to power minus 31 divided by 12, 10 into 10 raised to power minus 3 multiplied by 10 raised to power 6, which comes out to be, this implies lambda comes out to be 6.63 10 raised to power minus 38 meter. So when you compare these two things, right, this and this, we see that the wavelength for microscopic particle is way too high than for an macroscopic object, right? Hence we say that the wave nature is dominating at the micro level, and particle nature is dominating at the macro level, right? So deviations of both, right? So this is where we conclude for today. And in the next class, what we are going to study is the Heisenberg's uncertainty principle, right? So in this class, let us summarize what we have seen. So in this class, we have seen limitations of Bohr's model, right? Then we have seen the dual nature of particle, right? In this, we have seen that for microscopic, so we have confirmed the confirm particle nature and wave nature of electron using the Davison and German's experiments, right? Then we have also seen the de Broglie relationship. De Broglie relationship. Then we have calculated that using this de Broglie formula, that wave nature of particle of matter dominate at microscopic level, whereas particle nature of matter dominate at microscopic level, right? So this is what we have concluded, right? So here we can write Davison and Germer's experiment. So I thank you for attending this class, and I hope you have enjoyed and learned something from it, and I hope to see you again in the next class. Thank you.